Welcome back, everyone. In this video, we will examine a recent advance in quantum computing that has removed one of the most persistent obstacles researchers have faced. Quantum computers have been promising revolutionary gains in computation for more than 2 decades, but they've struggled to overcome noise and instability. A team working across MIT, the Niels Bohr Institute, and other leading research centers has published results that demonstrate a new method of real-time noise correction called frequency binary search. This method may enable quantum processors to move beyond the small experimental scale that has limited their usefulness until now. Please subscribe now. Quantum computing differs from conventional digital computing because it uses qubits instead of binary transistors. A qubit is a quantum state that can represent 0 and 1 simultaneously due to superposition. This ability to hold multiple states at once provides exponential potential for computation. However, qubits are quite fragile. Environmental disturbances, such as electrical fluctuations or vibrations, interfere with their coherence. Once coherence is lost, the quantum state collapses and the calculation becomes meaningless. Conventional computers do not face this kind of vulnerability, because transistors can reliably switch between 2 states without being influenced by microscopic noise. Researchers at MIT have explained that noise correction has been the single most expensive bottleneck in scaling up quantum hardware. The traditional process has required thousands of calibration measurements for each qubit. Even after long calibration cycles, the noise pattern changes faster than it can be compensated. The result has been that systems with dozens or hundreds of qubits could operate only briefly before error rates made them unusable. This made the idea of millions of qubits, which are required for powerful applications, seem unattainable. The new frequency binary search algorithm seeks to correct this problem in a way that scales efficiently. The principle of frequency binary search is similar to a narrowing technique in data science, where the range of possible values is reduced step by step until the solution is found. In this context, the algorithm rapidly identifies the frequency at which noise interferes with qubits. Instead of requiring thousands of individual measurements, it converges on the error condition in fewer than 10 steps. The system then applies corrections to the control signals that guide the qubits. This means that the time required for calibration is reduced from hours to seconds, and the adjustment can be performed continuously as the machine operates. The team at the Niels Bohr Institute emphasized that the method is universal. It's not restricted to a particular physical implementation of qubits, which is quite remarkable. Superconducting qubits, trapped ion qubits, and spin-based qubits all suffer from noise, and all can be corrected using this approach. That is significant because competing companies have pursued different technologies. IBM and Google have primarily focused on superconducting qubits. IonQ and Honeywell have worked with trapped ions. Microsoft has pursued topological qubits. Each design has advantages and drawbacks, but all must handle noise. A universal correction algorithm that can adapt to any platform reduces fragmentation in the field. To appreciate the improvement, it is helpful to recall how error correction has previously been managed. Classical error correction codes work by adding redundancy, so that corrupted bits can be reconstructed from surrounding information. Quantum error correction has attempted to mimic this idea by encoding logical qubits across many physical qubits. However, redundancy multiplies the number of qubits required by a factor of 10 or more. That cost has made scaling impractical. Frequency binary search does not rely on heavy redundancy. Instead, it makes the control process itself much faster and more precise, reducing the amount of redundant hardware needed to achieve a reliable calculation. Testing on real devices has been a crucial part of verifying the claim. The group integrated their algorithm with field programmable gate arrays, or FPGAs, that control qubit signals. Previous attempts at fast correction were slowed by latency in the control electronics. By using FPGAs placed close to the quantum processor, the correction can be applied in real time without delay. The demonstrations showed that decoherence times could be extended by factors of several hundred. That result was reported in peer-reviewed sources such as Science Advances and quickly gained attention across the research community. The practical consequences are quite large. With longer coherence times, more computational steps can be executed before the system fails. That opens the way to useful problem solving. Researchers at IBM have said that accurate simulation of molecules is one of the first valuable applications they expect from quantum computers. Current supercomputers cannot model the quantum behavior of large molecules because the calculations scale exponentially. With millions of qubits operating coherently, a quantum processor could design pharmaceuticals by predicting molecular interactions directly. This could shorten the drug discovery process by years and reduce costs by billions of dollars across the industry. Another example is cryptography. Modern public key encryption relies on mathematical problems such as factoring large numbers. Conventional computers cannot factor these numbers in feasible time, which makes the encryption safe. A large-scale quantum computer running Shor's algorithm could solve these problems rapidly. That would render current encryption methods obsolete. Governments, including the United States National Institute of Standards and Technology, have already begun preparing new post-quantum encryption standards. The arrival of real-time noise correction makes the urgency of that transition greater. If a machine with millions of qubits becomes operational by 2026 or shortly after, existing security infrastructures would need immediate replacement. Weather forecasting and climate modeling are additional domains that could see improvement. Present forecasts are limited by the inability to simulate complex atmospheric interactions at fine resolution. Quantum processors with noise correction could handle far more variables simultaneously. The European Centre for Medium-Range Weather Forecasts has expressed interest in integrating quantum resources once they become available. Accurate forecasts down to specific localities would improve agriculture, disaster preparation, and transportation logistics. These are examples of medium-term impacts, where governments and industry can already see the potential value and are planning to adopt the technology as soon as it is viable. In the financial sector, companies like JP Morgan Chase have been testing quantum algorithms on small experimental hardware. The ability to analyze large numbers of market variables simultaneously could enable predictions and optimizations that surpass classical methods. The limiting factor has been noise, which made results unreliable. With real-time correction, such applications could scale. Early trials reported in IE Spectrum have suggested that portfolio optimization problems that take hours on traditional systems might be solved in seconds with functional quantum hardware. As hardware progresses, these trials will shift from demonstration to real market applications. It is important to also state limitations. The algorithm addresses noise, but it does not remove all technical challenges. Building hardware with millions of qubits still requires advanced fabrication, extreme cooling, and stable infrastructures. Microsoft's pursuit of topological qubits is one approach to reducing fragility at the hardware level. Other groups are exploring error-tolerant qubit designs. Frequency binary search should be viewed as a complement to these efforts, not a substitute. Furthermore, scaling production of reliable quantum processors will require industrial investment comparable to that of the semiconductor industry. That transition will take years, even under favorable conditions. Universities and government programs are already moving to support these developments. In the United States, the National Quantum Initiative Act has provided funding for research centers at MIT, the University of Chicago, and other institutions. The European Commission has established the Quantum Flagship Program to coordinate work across member states. Japan's Ministry of Communications has invested in quantum networking projects that would link quantum computers together. Each of these initiatives recognizes that breakthroughs in noise correction accelerate the timeline. Planning for both scientific progress and economic adoption is underway at national and international levels. The broader implications of practical quantum computing extend beyond specific industries. The foundation of digital infrastructure could change in similar magnitude to the transition from mechanical calculators to electronic transistors. The companies that adapt first will have decisive advantages. In the 1990s, firms that ignored the internet found themselves obsolete. A parallel risk exists now for organizations that ignore quantum progress. IBM, Google and Microsoft are already building roadmaps that assume real-time noise correction will make large systems feasible. Other technology companies are likely to follow as commercial potential becomes clear. Looking further ahead, if machines with millions of qubits become standard, entirely new fields of research will open. For example, the study of materials at the quantum level could produce superconductors that work at room temperature. That would revolutionize energy transmission. Researchers at ETH Zurich have published papers exploring these possibilities, but they remain theoretical because of the limits of simulation. With noise-corrected quantum processors, those theories could be tested directly. Similarly, in aerospace engineering, NASA has investigated quantum methods for optimizing spacecraft design. Scaling quantum hardware would give them practical tools for this work. For the near future, the timeline is compressed. Before this breakthrough, many observers expected large-scale quantum computing to remain decades away. With frequency binary search, the schedule may accelerate. By 2026, we may see the first demonstrations of machines with millions of qubits performing useful tasks. That would mark the point at which quantum computing shifts from experimental science to applied technology. It is not guaranteed since fabrication and infrastructure challenges remain, but early results suggest that noise will no longer be the primary limiting factor. This has fundamentally changed the outlook across research communities. As with all major technological changes, workforce preparation is also necessary. Universities and private training providers are expanding courses in quantum information science. For example, MIT offers online modules for engineers who want to learn quantum programming. Private companies have begun producing toolkits so that software developers can prepare for quantum platforms. These efforts are essential since expertise is scarce. Without trained specialists, even the most advanced hardware cannot be deployed effectively. Reports in Nature Nanotechnology have highlighted the importance of education and skill development in parallel with hardware advances. It is instructive to compare this moment to the early days of the transistor. In the 1940s, electronic transistors replaced bulky vacuum tubes. The initial applications were limited, but within 2 decades they supported the microprocessors that defined the digital era. The Internet followed, creating a global network that reshaped economies. Quantum computing may follow a similar trajectory. Frequency binary search is the type of advance that moves a technology from fragile experiment to scalable system. While uncertainty remains, the parallel is strong enough that industry leaders are already making long-term plans based on the expectation of success. In conclusion, the invention of frequency binary search for real-time noise correction represents a turning point. It has been verified by respected institutions including MIT and the Niels Bohr Institute, and has been tested on real hardware using FPGAs. It enables qubits to remain coherent longer, reduces calibration time from hours to seconds, and scales universally across qubit designs. The potential applications span drug discovery, cryptography, weather forecasting, financial optimization, and materials science. The limitations of fabrication and infrastructure remain, but the key barrier of noise has been dramatically reduced. Thank you very much for watching. Please like and subscribe.